So, you've done it. You've trained a brand new machine learning model. That's awesome. But now comes the really big question. Is it any good? How do you actually know if your model's performing well, or if it's just guessing? Well, that's exactly what we're going to figure out.
Let's say we built a model to tell the difference between orange pumpkins and those kind of rare white ones. We hit run, it spits out some predictions, but how do we know if we can trust those results? Let's break down how we can get real confidence in what our model is telling us.
Okay, so before we can evaluate a model, we obviously need a model to evaluate, right? So first up, let's do a super quick recap of how we got our pumpkin predictions in the first place.
It's the standard playbook. You know the drill. We take our data, separate the features from the thing we want to predict, which for us is the color, and then we split that data into two piles. We use one pile to train the model, and we keep the other one locked away to test it later on data it's never seen. After it's trained, we let it make its predictions, and we get a list of zeros and ones. Pretty straightforward. So, what now?
Now that we have our predictions, the first thing most people do is check the accuracy. It's intuitive. But I'm warning you, this simple metric can hide a really big problem. I like to call it the accuracy trap.
Accuracy is, well, exactly what it sounds like. It's the fraction of predictions our model got right. If it made 200 predictions and got 180 of them correct, that's 90% accuracy. Simple, clean, and it feels like a great way to score our model. But, as you're about to see, simple isn't always best. And here is where the plot thickens. The accuracy trap snaps shut the moment your data is unbalanced. That just means one category shows up way more often than the other. And this isn't some weird niche problem. This happens all the time in the real world, like with fraud detection or medical screening. And if we look at our pumpkin data, we see this exact problem. About 83% of our pumpkins are your standard orange, while only about 17% are white. Our dataset is heavily skewed towards orange. So here's the crucial part. What if we built a lazy model, a model that doesn't even bother to learn anything and just predicts orange every single time? Well, since 83% of the pumpkins are orange, it would have an 83% accuracy score. On paper, that sounds pretty decent, right? But in reality, it's completely useless. It has zero ability to find even one white pumpkin. Accuracy on its own has totally let us down.
So if accuracy can lie to us, how do we get the real story? We need a better tool. We need something that shows us not just if a prediction was right, but how it was right or wrong. And for that, let's bring in the confusion matrix.
Now don't let the name scare you. A confusion matrix is just a simple little grid that organizes our predictions. It compares what the model predicted against what was actually true, and it sorts every single prediction into one of four boxes. This helps us see exactly where the model is succeeding, and, maybe more importantly, where it's getting confused.
Let's start with what happens when our model predicts white. That's our rare or positive class. If the model says a pumpkin is white and it was actually white, that's a perfect match. We call that a true positive. But if the model predicted white and the pumpkin was actually orange, that's an error. We call that a false positive.
Now for the other side of the coin. What if our model predicts orange, our common or negative class? If the pumpkin was truly orange, great, that's a true negative. But the most important type of error is when the pumpkin was actually white and our model missed it and called it orange. That's a false negative.
Okay, let's plug in the actual numbers from our pumpkin model. See that diagonal, the 162 and the 22? Those are our wins, our correct predictions. The other diagonal shows the mistakes, 4 false positives, and here's the key part, 11 false negatives. This tells us we successfully found 22 white pumpkins, but we completely missed 11 of them. This is so much more revealing than a single accuracy score.
So the real power of the confusion matrix is that it lets us calculate much smarter metrics that tell us a richer story. Let's talk about the two most important ones that come from these four numbers: precision and recall.
Precision and recall answer two very different questions. Precision asks, when our model pointed and said, "That's a white pumpkin," how often was it right? Think of it as a measure of quality. Recall, on the other hand, asks, of all the white pumpkins that were actually out there, how many did our model manage to find? This is a measure of quantity, or completeness.
And you can probably see there's a natural tension here. A model could get perfect precision by only flagging the one pumpkin it's absolutely 100% sure about.
but it would have terrible recall because it missed all the others. The key is that neither one is better, they're partners, and they're both equally important for evaluating your model. So, if we need both precision and recall, it's kind of a pain to track two numbers. Wouldn't it be great if we could just combine them into a single, really meaningful score? Well, we can. And that brings us to our final and most powerful metric, the F1 score.
The F1 score is basically a very clever average of precision and recall. It's their harmonic mean, which is just a fancy way of saying it gives more weight to the lower value. This is fantastic because it means a model has to be good at both precision and recall to get a high F1 score. You can't cheat the system by being good at one and awful at the other.
Now, a lot of reports will also show you a macro and a weighted average. Just think of these as different ways of looking at the overall score. The macro average is great if you care about performance on all classes equally, no matter how rare they are. The weighted average gives more influence to the bigger class, so it kind of reflects the dataset's imbalance. They both just add a little extra context.
And this is really the central idea to take home today. When you are looking at an unbalanced dataset, you've got to step away from simple accuracy. The F1 score is your new best friend. It gives you that single, reliable number that gives you a true sense of your model's quality.
So we've gone from a single misleading number to a full grid of insights and all the way to the powerful F1 score. But these are all still just numbers. What if we could actually visualize our model's performance in a single, intuitive chart? I mean, numbers tell us part of the story, but could a picture tell us even more? We'll find out.